Okay, first question. What is the probability of flipping a coin tails 4 times in a row? Everybody put your phones away. Who can tell me? 1 over 8? No. 1 over 16 is correct. Okay? The probability of getting a tails 4 times, right? Well, that's a 1/2 probability tails for the first one, 1/2 probability tails for the second one, 1/2 probability tails for the third one, 1/2 probability tails for the fourth one. 1 out of 16, which is what percentage? 0.0625. There's only a 6% chance that anybody, starting from right now, flips a coin and lands 4 tails in a row. Okay? Here's the second question. What is the probability that in 20 coin flips, you will flip tails 4 times in a row at some time? Okay? This I can calculate. 6% chance. This seems a little bit trickier to calculate.
Wouldn't you do that times 5?
Do this times 5? Because it's like the first 4, the second 4, the third 4. Well, maybe you do, it's not as simple as that, right? Because maybe you do a heads and then 4 tails. Right? So this seems complicated, right? Do we think it's going to be more likely than 6%? Maybe it's probably the same as 6%. I don't know. Question?
Well, how is that different than whenever we have problems with, like, in a 25-question test, what is the probability that you get, the first 3 wrong?
Well, because it's being very specific. It's saying getting just 1, 2, and 3 wrong.
I know. That's why I was like, that's mine.
Right. This, putting it out like here, says we're going to get 3 wrong in a row somewhere in a 20-question test. Here, we're going to get 4 tails in a row somewhere in 20 flips. Okay? You can calculate this. We could spend the rest of the semester going over different counting techniques and different probability theorems to be able to mathematically calculate the actual percentage chance of this happening. Okay? But it's very, very complicated. I'll just say it right now. So instead, we're going to do something else. We're going to be able to try to find the answer to this question by simulating this occurring. Okay? Instead of trying to calculate theoretically the mathematical probability of this, instead, we can use all of us, and all of us can flip a coin 20 times, and we could see who out of all of us succeeded and who failed. And we could see, oh, hey, turns out, 1 or 2 out of the 32 of us, how many are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There's 25 of us. Well, if we did number 1 right now, and let's do this right now, if there's 25 of us, and only 6% of us, there's a 6% probability that we will flip 4 times in a row, I bet you between 1 and 2 of us will flip or roll a die and have it land as an odd, which will count as a tail, 4 times in a row. Okay? That we can do. And I bet you the amount that we get is going to be close to 6%. So let's do that. Let's go, and you will flip your coin 4 times in a row. Once you land on a heads, you're out. Okay, you got to be honest. All right, here you go. Ready, set, first roll. I'm out. Okay, ready, set. Even is head, odd is tails. Ready? Who's still in? Should be half of you. Supposed to get nods. Okay? Okay. Ones who flip the tail correctly, do it again. Go. If you flipped another odd, ready, set, go. If you flipped another odd, last one, go. Did you get it? 0. So far, 0 out of 25 of us have succeeded. But let's try again. Ready, set, first flip. I fail again. Ready, set, second flip. Ready, set, third flip. Ready, set, last flip. 0 out of 50 of us. Let's do it again. We'll do it 2 more times so we get 100 trials. Ready, set, first flip. I'm out. Ready, set, second flip. Ready, set, third flip. Ready, set, last flip. All right, what? 1 out of 75 of us has gotten it. Last try. Ready, set, first flip. I'm out again. I've gotten heads every single time. Ready, set, second flip. Ready, set, third flip. Ready, set, last flip. 2 out of 100. Okay, if we kept going, what we would find, I don't want to spend that much time doing this, is that our experimental probability would get really, really close to our actual probability, right? This is what we would call our experimental probability. This is our theoretical probability. This would eventually match this, okay? For question number 2, put your phones away. We don't have the theoretical probability. But let's just say, screw it. It's too complicated. I want to get into it. If we do trials and if we simulate it and we look at our experimental probability, what we will find is that as long as we do enough trials, we will find pretty much what the answer to the theoretical probability is going to be. Okay? Instead of worrying about the theoretical side, we'll go straight to the experimental side. So, I don't know what the probability is, but everybody's going to do this. I want everybody to flip their coin 20 tries. When you flip tails, start counting on your head, on your hand, how many tails in a row you flipped. Not on your head. You can do your hand on your head. I like to keep like the number of counts of flips in my head. I count to myself. And then when I flip a tails, I start counting 1. And then if I flip another tail, 2. And then 3. It's got to be 4 in a row. So once you do, 2 tails and then you flip a head, you go back to 0. Okay? Let's see who can succeed in flipping tails 4 times in a row sometime in the 20 coin flips. Ready, set, go. Once you get it, you're done. Yay! I did it. Yep.
And you're like in a row, you did it? Four.
No, just somewhere in 20 throws, at some point, you get 4 in a row.
I did 4 in a row. I thought it was just did it.
At some point, if you're rolling it 20 times, you'll get 4 in a row. Try it.
I did, and I got it one time.
Then you're good. Yeah, you did it. You thought it was going to be hard?
I thought it was like 4.
No. It's getting
I mean,
tail, odds at some point in 20 throws. Okay. Now, in the 20 throws, and last time I only did this, I didn't do it at all. In the 20 throws, who succeeded in getting 4 tail/4 odds in a row? 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Anyone get it twice?
No, we don't care. Okay, well, 11 out of 25 of us got 4 in a row. Let's do it again. Now, be honest. Remember, count. You only get 20 tries. You only get 20 tries. See if you can get 4 tails in a row somewhere in the 20 tries. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Boom. All right. Is that 20 tries? Okay, yeah. Who succeeded this time in getting 4 tails in a row somewhere in the 20 flips? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of us. So we're going to add 13 and add 25. Now we're at 24 out of 50 of us. Let's do it again. Thank you. Go. Yes. Watch the video online. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I did it again. Okay. Who succeeded this time? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to do it one more time to get 100 trials. Ready, set, go. 4, 5, 6, 7, 8, 9, 10. Who succeeded? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Notice our numbers of successful trials are almost crazily consistent. 11, 13, 10, 13. This is going to be 47 out of 100. Okay? Experimental probability, right here. Every single one of these is experimental probability. As I do more and more trials, more trials, we would get an experimental probability that would get closer and closer to the theoretical probability. We don't have to find the theoretical probability mathematically. We can say, most likely, the answer to this question is around 50%. Which seems crazy when you think about if I just give you 4 throws, it's only a 6% chance that you will throw tails 4 times in a row. Well, if I say, well, do it sometime in 20 throws, all of a sudden it jumps all the way up to there's a 50% chance around that you are going to get 4 tails in a row somewhere in 20 throws. This is essentially what we're doing this unit. We're saying throw the theoretical probability out. Don't worry about these calculations. Take harder probability problems like this and let's simulate it. And let's use experimental probability, and the experimental probability will help us answer this theoretical probability or give us a decent enough idea of what is going on. Okay? Now let's look at your notes. Notice the back of your notes. What we're going to be doing is not rolling die all the time. You know, we're not going to be flipping coins all the time. We'll be talking about stuff like a person's making 75% of his free throws. Or there's a 30% probability of this. So there's a 20% probability of this. And instead of rolling die to simulate things, we're going to be using random number generators. Okay? Now, we could have done the same exact trial that we were just doing with our die using this random number generator. I could have said, take a one-digit number, 0 through 9. If I get an even, 0, 2, 4, and 6, and 8, that's 5 possibilities. That's ahead. If I get an odd, 1, 3, 5, 9, 1, 3, 7, 5, 9, thank you. There's 5 possibilities. That's 5 out of 10 chance that I'm going to get a tails on any random digit. Well, let's see me do that on this line. I could say, okay, this is a tail. Ahead, 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 a tail. Tail, tail. Ooh, close to getting 4 in a row. Head, tail, head, tail, tail, head, tail, head. That's 15. I got 4 more. Head, tail, head, head, head. I failed. I didn't get 4 tails in a row. But notice how it's like I can quickly do that with numbers. Well, let's say I have one of these cheap dice, or if I have a cheap coin. Okay? Let's say I have a cheap coin, and on this cheap coin, heads pops up 60% of the time. And tails pops up, well, why don't we say heads is 40? And tails will pop up 60% of the time. What's the probability that we'll get 4 tails in a row now? That's going to change the entire question. But what can I do using these numbers to maybe simulate a cheap coin, a weighted coin? Any ideas on how I could use numbers to simulate a weighted coin?
on a die.
I'm using numbers.
Well, you're being biased, so all you're saying is represent
Mr. Englander, you said odds and 2. So we said 50-50 shot, odds, tails, evens, heads. Well, Mr. Englander's just said add another number to the odds so that there's 6 total numbers that would represent a tails, and then the rest would be heads, and boom, now we've gotten it. Well, let's make it easy on ourselves. Instead of doing odds and 2, why don't we just say 0, 1, 2, 3, 4, and 5. That'll be a tail. And then 6, 7, 8, 9, that'll be a head. Well, now let's do the trial. Here is my trial for a weighted coin. I would get a head, a tail, head, tail, head, tail, 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 boom. I did it. My probability went up. Because in the last problem, that 5, or the number's a little bit different, but you know, this kind of takes into account my uneven probability. Instead of odds and evens, I now have numbers 0, 1, 2, 3, 4, 5, which is a total of 6 numbers out of 10 single digits, and boom, I get it. Okay? This is the idea. We can represent probabilities, percentages, using numbers, and we can use a random digit table to do these trials instead of working with die or other things. And now we can answer tough probability questions. What if I change this to a 65% chance that a tail will flip up, which means heads is 35? What could I do with my table of random numbers to represent a 65% chance? Tougher, right? Like I can't do 0, 1, 2, 3, 4, 5, and 5.5. You know, that doesn't work. So no, that would kind of, you can't have 2 results both happening.
Every other 6 that comes up, make it a.
No, I don't want to do with every others. I want to just kind of say, you know, these are going to be heads and these are going to be tails.
You do it in like increments of 2.
So you're saying 2-digit numbers. 2-digit numbers. That's interesting. Well, what numbers could I use for, you know, heads or tails if we're using 2-digit numbers? So I could use 1 through 35 and then 36 through 100, but then all of a sudden I have a 3-digit number.
0, 1 through 99. 0, 0 through 99.
Oh, so maybe instead of 1 through 35, I should go 0, 0 to what?
35. 34.
34. Because 0, 0 through 34 would be 35 total numbers, and then 35 through 99, that would be 65 total numbers. And now I can look at 2-digit numbers, and that would represent these coin flips of this really weird weighted coin. So I could say 72, that's a tail. 82, tail. 95, a tail. 2, that's a head. 32, that's a head. And so on and so forth. And all of a sudden, I am simulating a weighted coin, which is really cool. Can't do that with a die. Can't do that with a coin. Okay? And this is what we're doing. We're going to be able to simulate things of different probabilities using random number digits. Let's go to our front. Let's talk about it. Do some quick notes. Simulations are great. Simulations are going to work well when we are going to try to calculate mathematical probability that is difficult or complicated, and we don't know how to do it. Instead, we will go straight to a simulation to kind of have the general understanding of whether it's unlikely or equally likely or not to happen by doing a simulation. Just like, turns out, and you could tell your friends, there's a 50-50 chance that if you flip a coin 20 times, you will get 4 tails. You know that now, because we did enough simulations that you could say that. Okay? This is, don't even worry about this. This right here and this. Here's how we're going to simulate. There's a 4-step process. The steps are simple to understand. It's really, the first thing we got to understand is what we were just doing on the other problem. What we were doing on the on the other side was step 1, assigning digits to understand probabilities. Okay? Assigning digits is step 1. And if we had probabilities that were multiples of 10, like a 50-50 chance or a 60-40 chance, we can use a 1-digit number from 0 through 9. So if I want to do a 20% chance of something succeeding, I can say use 0 and 1 as a success and use 2 through 9 as a fail. Zero through 1 would be represented by the 20%. This would be the fail. Okay? If, however, my probabilities were not multiples of 10, like if it was a 65% probability, a 12, a 95% probability, we need to use 2-digit numbers, like Mr. Englander figured out. And we should start at 0, 0 and go to 99. An example is like a 32% success, so like a probability of flipping a head on a weighted coin being 32%. I would go from 0, 0 to 31. And I don't even have to go from 0, 0 to 31. As long as I had 32 numbers between 0 and 0 and 99, and I'd say those numbers are a success, well then you can use those numbers and all the other numbers would be fails. 32 through 99 would be a fail. If you have probabilities that have decimals, like 15.5, 20.3, you need to use 3-digit numbers, okay? From 000 to 999. We will be able to also produce random numbers between 2 numbers on our calculator. Using random integer, we'll show you that in the future, okay? You'll go to Math, PRB, random integers between a first number and a last number, and the amount that you need. Okay? Now, here's an example. If we want the probability of a success, always think of a success as like doing something and getting what you're looking for. Like I want to flip a tail. 8% success rate would be like there's an 8% chance that I'm going to flip a tail. Question is, which of the following random digits could be used for the assignment of the random digits to the success? Well, let's see. If 0 through 7 was a success, how many total numbers is that? 0 through 7.
How many total chances?
How many numbers are 0 through 7? 8. 8 successes. 8 through 9 would not be successes. Well, that means success would be 8 out of 10. And not success would be 2 out of 10. Would that represent an 8% probability? Would we use this for an 8% probability? No, because this is an 80% probability. So I would say, no, don't use this. What if we said 0 through 8 was a success and 9 was not a success? Well, 0 through 8 is a total of 9 numbers. 9 is one number. That'd be 9 out of 10 successes. 1 out of 10 would be a fail. Does this represent an 8% probability? No, so we wouldn't use that. Well, what if we go from 0, 0 to 0, 7 as a success, and we go from 0, 8 to 9, 9? Would that represent an 8% probability of a success? Yes or no, Mr. Englander? Yes is correct. This is 8%. Thank you very much. Okay, so that, boom. Now I can represent something that has an 8% chance of success, because we have a total of 8 numbers out of 100 possible numbers. 92 through 99. How many numbers are in 92 through 99? Let's see. 92, 3, 4, 5, 6, 7, 8, 9. How many numbers is that? 8 numbers. Sweet. 0 through 91. How many total numbers are in from 0, 0 to 91? 92 numbers. Total of 100 numbers. 8 out of 100 would be succeeding. 92 out of 100 would be failing. This would also represent an 8% chance of succeeding. What if I did 0, 0 through 0, 5 and I added 98 and 99? 0, 1, 2, 3, 4, 5, 98, 99. That's 8 numbers. 6 through 97, that's got to be 92 numbers. So that's 100. This also could represent an 8% chance. I'll tell you, any of those could be used, but just for our class, just keep it easy on yourself. Go from 0, 0 to 1 less than your probability, and that will be that will always work. And then the remainder will be something not succeeding. The second step is called the stopping rule. We have to understand how many trials or how many times, how many numbers we're going to look at. Step 3 is you're going to count. You're going to understand which ones succeed, which ones don't succeed, how many trials that we're going to do, how many trials. Okay, so the digits, how many numbers we're going to look at, how many trials we're going to do, and then we're going to just go for it. Simulate and look at results. Okay, let's go to our first situation where the theoretical probability is going to be tough to calculate, so we're going to simulate it. We have a basketball player who, over the course of her long career, has made 75% of her free throws. You could say the probability of her next free throw is 75%. Okay? In a tournament game, so this is the final game of her career, possibly. Let's just call it the championship. In the tournament championship game, she's shooting 5 free throws. For some reason, she got fouled on a 3-point play and also got fouled again on a 2-point play right after that. So she's shooting 5 free throws late in the game, and she misses 3 of them. The fans think she was nervous and she choked. But you think, because you're a statistician, that the misses may simply be due to chance and that it's okay that you miss 3 out of 5 if you're a 75% free throw shooter. Okay? The question is, what is the probability that the player will miss, or any player who's a 75% free throw shooter will miss 3 or more of the 5 shots? Now, if I asked you that question and I asked you to answer this question in a theoretical sense, you would have a tough time. You do not know the counting principles to be able to answer this theoretically. So instead, you're going to be like, hold on, Mr. Messner, I need to kind of simulate this. I'll get back to you. We're going to simulate this to estimate this probability. Hopefully our estimation will help us understand the theoretical probability. We want to do a total of 12 trials. All right, here we go. This is important. Step 1, where you're going to sign the digits. There's a 75% chance that this person, this girl, this great basketball player is going to make a free throw. What numbers would I use for a made free throw? If there's a 75% chance that she's going to make. Thank you, Mr. Funk. 0, 0 to 74. Which means the other numbers, 75 through 99, are going to represent a miss. Step 2, we're going to see how many numbers we're going to do. Or how many numbers do we need? How many numbers do we need each time? 5, right? We're looking at somebody who's shooting 5 free throws. Step 3, we're going to figure out how many trials. How many trials does this question want us to do? 12. We're ready to start. We are going to simulate a 75% free throw shooter making and missing free throws. Here is the first trial. I'll do it, and then we'll just finish off the rest. You can do it by yourself. 72, made or a miss? Make. 89, miss. 95, miss. She's missed 2 so far. 2, make. 32, make. I can say she missed 2. Keep going. Do this 12 times. You can either count up how many she made or how many she missed. We're looking for when she misses 3 or more. So you're looking for, 3, 4, 5 misses. Keep going. We're doing 5 free throws in a row. Okay? We're looking at just a set of 5 free throws. So 1, 2, 3, 4, 5. What's up?
How far do we go?
We're going to go until we've done this 12 times. I've only done it once, twice, 3 times.
That's what I'm asking. So a set of 5 is like 1 trial?
Yep.
Okay.
Yep. Make, miss, make, miss, miss. She missed 3 this time. Why don't we stop at 8 if we've done 8 already? Confer with my results. I've gotten 2 misses, and 2 misses, and 4 misses, and 2 misses, and 1 miss, and 3 misses. This will be... Okay, that's good. So this is how many? 1 miss. And this is 1 again. Thank you. Okay. So we just did this simulation. And out of 12 total 5 free throw trials, how many of them missed 3 or more? Only 2. 2 out of 12 missed 3 or more. Now, I'm comfortable with 12 trials, but what would make me more comfortable with my results? What could I do to have my results be stronger? Thank you. More trials, better results. Okay, so that is a 1 out of 6 chance in this situation, or a 0.1667. So I say that the probability that somebody who's a 75% free throw shooter, that they miss 3 or more out of their 5 shots is only 16%, 16% chance. Do you think that this great female basketball player, her missing 3 of the 5 shots is due to chance, or maybe she choked? Probably choked, right? Because it's unlikely, based off of our simulation, that this occurs. Unlikely to occur. Player probably choked. Okay? We have a good understanding of a situation that might seem complex. Second one, the percentage of women in the labor force of a certain country is 30%. A company employs 10 workers, 2 of whom are women. Okay? Because of this, the women want to sue for discrimination. They feel like they are underrepresented in their workforce of 10 people, and that they should have more women in the workforce. This is what they're saying. Okay? The government hires you. They say, hey, you, tell me, do they have a case? If having 2 women out of a 10-person workforce, is that unlikely if there's a 30% chance that if 30% of the workforce is female? Okay, how unlikely is it to occur if 30% of the workforce is female, for there to just be 2 out of 10? Okay, let's find out. You say, I don't know right now, let me get back to you. First, we're going to assign. We're talking about females and males. 30% of the workforce is female. What numbers could I use to represent a female? Mr. Riley. You can use 0, 0 through 29. Perfect. That's 30. However, there's an easier way to do it since it's a multiple of 10. Anybody? 0 through 3 would be 4. 0 through 2. If I get 0, 1, or 2 in a one-digit number, this is going to be a female. If I get 3 through 9, that will be a male. We have 10 workers. So we're going to look at a sample of 10. The amount of trials that we're going to have. 10 runs of the simulation. 10 trials. Go. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 digits there. How many of these 10 digits will be female? 0, 1, or 2. 1, 2. 2 females there. Next one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many females do we have? 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. 1. 1, 2, 3, 4. 0. 1, 2. 1, 2, 3. 4. 1, 2, 3. There's my 10 trials. Based on your simulation, estimate the probability that a company of 10 workers would employ 2 or fewer women just by chance. 1, 2, 3, 4 out of our 10 simulations, 4 of our companies had 2 or fewer women, which means that on a given random simulation, there's a 40% chance that you will have 2 or fewer women out of a 10-person company. So, these women at this company who want to sue, do they have a case? Yes or no?
Well, compared to the other ones, they are under the 50%.
They are under the 50%, but is it likely, somewhat likely, by chance, to just have 2 out of 10 women? I would say yes, kind of. You would say there's a 40% chance that you could get 2 out of 10 women by chance. I would say, no. 40% chance or 40% probability just by chance. If it was closer to like 20 or 10, I would say yes, they are underrepresented. It's very unlikely to have 2 or less women. Kind of want, to be around 50, but we won't see that unless we look at 3 probably. Okay, last question. This is the question always asked with tough theoretical probability questions that we can always try to explain using experimental probability. The case of the duplicate birthdays, okay? If there are 30 students in a class, don't worry about this betting. Don't worry about the betting. The question is, what is the probability that 2 of the students were born on the same day of the year? Okay? So 30 students, probability that 2 students were born on the same day. How likely do you think that it is to occur, Mr. Champagne? Pretty unlikely, right? All right, I'm going to go around. We have 25 people. Okay? Let's see if any of us share the same birthday. You're just going to say your birth date. If somebody has your same birth date, just stop and we'll all cheer. Okay? Ready? Go.
June 1st, 29.
June 1st,
November 29th.
November 29th, December 27th, August 29th.
October 17th.
Oh my goodness, what's your birthday? October 17th and your birthday? October 17th? That's incredible. There's 2 people in this class with the same birthday. What are the odds of that? We want to keep going? 2 people? All right, Miss White. December 19th.
January 29th.
January 29th.
September 6th. Yeah, right here.
Oh my goodness! What is going on? 2 pairs of people with the same birthday? This must be the luckiest class ever. Should we keep going? This is crazy.
June 10th.
June 10th,
June 11th. Oh, whoa.
June 2nd.
June 15th. October 17th.
Oh, okay, right. All right.
January 5th.
November 17th.
March 22nd.
September 6th.
April 11th.
August 18th.
May 25th.
April 15th.
Okay. We know we're already past halfway. Okay. Well, that's crazy. 2 pairs of us have the same birthday. What are the odds we must be the luckiest class? Well, it turns out it's actually a 50-50% chance. If you have 30 people in a class, that 2 of them are going to share the same birthday. We can simulate that. Okay? Everybody get a calculator out. Turns out it's not that crazy to have the same birthday if you have enough people in your class.
Yeah, my sister's
Yep.
birthday is January 6th.
Okay, everybody get a calculator. Here's how we're going to simulate this process of having 30 people in a class. You are going to pull up a set of 30 random integers, and there are 365 days in the year. Let's see if we can just do a random integer between 1 and 365. Okay, now how do you get the random integer? You go to math and then over to PRB. I'm going to do it on my calculator as well. And we want 30 of them. Everybody needs to do this for us to get good results. No, just start from 1 to 365. That's 365 numbers. Okay, so math, scroll over to PRB, go to ran integer. This is how your calculator can produce random integers. You go from 1 to 365. So that's a comma.
How do you do it?
Comma is above 7. 1 comma above 7, 365 comma, and then you're going to say, give me 30 numbers. Okay? Now press enter and you should get 30 numbers. Let's see your commas again. Oh, if you have the same numbers, it's because we have the same, no, the same kind of seed. No, you shouldn't get decimal points. All right. Here we're going to do, we're going to store this in L1. Press store down here. Store in L1. L1 is second 1. Are we there? Anybody need time for that? Store L1, enter. Now, just reset the calculator.
Okay.
So I can plus 712. Okay, now go into stats. Go to sort A. Go to stats. Go to sort A. You need 365 of these random, you need 30 of these random digits.
Oh, I didn't know.
Okay, store in L1, stat, sort A, and you're going to do sort A, L1. Type in L1.
How did you store it?
Store L1. Store L1. Then go to stat, sort A, L1. Okay.
Sorry. I think I have to clear my.
Sort A, L1. Now, ready? Who's still with me?
Can we go?
Yeah, go ahead. Okay, if you're still with me, go into stat, go into your edits. If you see two numbers that are the same number, that's like having the same birth date. I have two numbers, my first two numbers are 3 and 3. That means two people in my class of 30 have the same birthday. Yeah, but we had two, yes, right.
Wait, do we remember how to do this? Or?
No, this is just the simulation for us to see how it's actually fairly likely, not super likely, but there's a 50-50% chance that we're going to find a class with the same number. Who found a class with the same numbers? Who didn't? Who didn't? Good. See, we have some that didn't, some that did, 50-50% chance. Okay? When you go to your next class, try it out. Ask people their birthdays. And you'll find that it's more likely than you think it would be.
Some people, and then it makes me do like friends because I don't really know them. Can I use your restroom?
Yep.
Yeah, I can use the restroom.
Yep.
Yeah, I'm sorry. Oh, I just.
Yes.
Can I go to
Sure.
Oh, us, like me and Sam.
Okay. What's up, Mitchell? Of what? Of what?
These are huge drives.
All right. They're not cheap.
We should have used these.
They're not cheap. Oh, get the worksheet on your way out.
Oh, is that the homework?
That's the homework.
Get one for me.
They'll be okay.
I'll be okay.
All right, the three of you.
Thank you. I think how many did we have last time? Okay, I'm missing two. I only have.
That means you're just excused because you're absent those days.
Okay. All right. So.
Are you ready to take the test now? Or do you want to take it like tomorrow morning or something?
I'm gonna take it tomorrow morning.
Okay. Okay, that's fine. Tomorrow morning. Sounds good. Sure.
What time do you?
7:45. It's not a long test though, so if you get here at 8, you probably should be fine. Okay.
So these are like filters on this Good Boost website, like different filters for like stock.
Filters.